Assalamualaikum and good morning everyone. My name is Muhammad Faris Muhammad Faisun. Today our group will be presenting a mechanics of material case study on the collapse of the Silver Bridge, which occurred in the United States on December 15th, 1967. The Silver Bridge collapse is considered one of the most significant bridge failure in engineering history because a single structure component failed, causing the entire bridge to collapse within seconds. In this presentation, we will first introduce the bridge and the specification. We will then discuss how the bridge failed and analyze the failure using important mechanics of material concept such as cross-sectional geometry, bending moment, maximum stress, yield stress, and bending curvature. By understanding this case study, we can see how engineering principles directly affect the safety and reliability of real-world. But before we begin, let me briefly introduce our group members. Alongside me, we have our group lead, Presenter Jianwei, and also other fellow presenter Ashraf Bazli, Muhammad Hairul Hakim, and Nur Amni Fayadah. Our case study focuses on the catastrophic collapse of the Silver Bridge in 1967. Although the bridge stood successfully for nearly 4 decades, a small defect eventually caused one of the most devastating bridge failures in history. Through this presentation, we aim to explain not only what happened but also why it happened from engineering perspective. The Silver Bridge was a suspension bridge complete in 1928 and constructed across the Ohio River in the United States. It connects Point Pleasant in West Virginia with Cayuga in Ohio, serving as an important transportation route between the two states. At the time, the bridge played a significant role in supporting the movement of people, vehicles, and commercial goods. It was considered an important part of the local economy because it facilitated trade and transportation across the river. For many years, the bridge served as a major connection for daily commuters and freight transport. The Silver Bridge had a total length of approximately 680 meters and remained in operation for 39 years. However, it is important to remember that the bridge was designed during the 1920s. During that period, vehicles were generally much lighter and traffic volume was significantly lower compared to the modern standard. As the year passed, the number of vehicles using the bridge increased, and the average vehicle weight became much heavier. This meant that the bridge was exposed to loads that were much greater than those originally anticipated by its designer. On December 15, 1967, during the evening rush hour, the bridge collapsed into the Ohio River. The collapse resulted in the tragic loss of 46 lives and shocked both the public and the engineering community because the bridge appeared to function normally before the incident. Engineers began extensive investigation to understand the exact cause of the failure. Now, let us look at the specification and structural design of the Silver Bridge. The Silver Bridge was classified as a suspension bridge and was primarily constructed using carbon steel. One of its most unique features was its I-bar suspension chain system. Unlike modern suspension bridge, which use thousands of steel wires bundled together to form large cable, the Silver Bridge relied on steel I-bars connected through pin joints. This design was considered innovative at the time because it reduced construction costs and simplified manufacturing and assembly. The bridge had a main span of approximately 213 meters and a total length of around 680 meters. The structural system consists of steel I-bar that carried the load from the roadway to the supporting towers. Although the design was efficient and economical, it had a major weakness. Modern suspension bridges usually have a high degree of redundancy, meaning that if one of the components fails, other component can continue carrying the load and prevent total collapse. However, the silver bridge had very little redundancy. Each suspension link consists of only two I-bar. This meant that the failure of a single critical member could severely compromise the stability of the entire structure. In other words, the safety of the bridge depends heavily on every individual I-bar, remaining intact throughout its service life. This lack of redundancy would later become one of the key factors that contribute to the collapse of the bridge. With that understanding of the bridge background and design, I will now hand over to the next presenter, who will explain how the bridge failed and the factors that led to the collapse.
Hi everyone, my name is Brandon, and right now I will be explaining about how the silver bridge actually failed and also the factors that led to its ultimate collapse. Although the bridge appeared to be stable and strong from the outside, investigations after the disaster revealed that the collapse actually began with a very small crack inside one of the steel I-bars. So at first, the crack is microscopic and it is extremely difficult to detect during routine inspections. However, over many years, the bridge was subjected to repeated traffic loading. So which means every time vehicles cross the bridge, the I-bars experience a cycle of loading and unloading at the same time. So this repeated stress gradually weakened the material through a process known as metal fatigue. And also you may ask, why does metal fatigue and how does metal fatigue cause such a big collapse, right? So metal fatigue actually occurs when a material is repeatedly stressed over a long period of time, which in this condition it causes small cracks to slowly grow even when the applied stress is lower than the material's ultimate strength. So moving on, there are actually several factors which contribute to the growth of this crack. The first factor was that stress concentration around the pinhole connections. As explained earlier, the I-bars contain holes for the connecting pins. So these holes created areas where stress became, very concentrated. It is all focused at that one point, making them the most vulnerable locations for crack to form. And the next factor, we have corrosion. Over many years of exposure to environmental conditions, corrosion weakened parts of the steel and also made crack growth more likely.
Assalamualaikum and thank you, Brandon. Now I will be presenting the mechanic material analysis of silver bridge collapse. Specifically, I will focus on the cross-sectional geometry of the I-bar, the concept of stress concentration, and how this factor contribute to the eventual failure of the bridge. To understand why the crack formed and propagated, we first need to examine the shape and the design of the I-bar itself. The silver bridge used an I-bar suspension chain system rather than conventional steel cable system that is commonly used in a modern suspension bridge. An I-bar is essentially a steel tension member with enlarged ends that contain circular holes. These holes allow the I-bar to be connected together using large steel pins to create a chain-like arrangement that transfer load from the bridge deck to the supporting towers. From a structural perspective, the I-bar was designed with a flat rectangular cross-section along most of its length with a large circular pinhole at each edge. This design was considered efficient during the 1920s because it simplified manufacturing and reduced construction costs. The pin-connected system also allowed the bridge to accommodate small movement and deformity caused by changing loads and environmental conditions. However, although this design offers several advantages, it also introduces a significant structural weakness. When a hole is created in the structural member, the effective load-bearing area is reduced. According to the basic stress equation, stress equals force divided by area. This means that when the same amount of force is applied to a smaller cross-sectional area, the stress experienced by the material increases. In an ideal structure member without discontinuities, stress is distributed relatively uniformly across the entire cross-section. However, the presence of a hole disrupts this distribution. Instead of flowing smoothly through the material, the stress line becomes distorted and concentrated around the edge of the opening. This phenomenon is known as stress concentration. Stress concentration occurs when there is sudden change in geometry, such as holes, notches, sharp corners, or cracks. These discontinuities cause localized regions to experience stress that are significantly higher than the average stress acting on the member. In the case of the silver bridge, the highest stress concentrations occur around the inner edge of the pinhole connections, even though the average stress in the eye-bar might have been within acceptable limits. The localized stresses near these regions could be several times greater.
Assalamualaikum and thank you Ashraf. I will now present the engineering calculation and analysis related to the silver bridge collapse, beginning with the bending moment analysis. To understand the force acting on the bridge, we first need to analyze the bending moment generated by the traffic loads. When vehicles travel across the bridge, their weight acts as a load on the structure. For this analysis, the traffic load is assumed to be uniformly distributed load acting along the bridge span. This load generates internal forces within the bridge members, causing them to bend. This bending effect is represented by a quantity known as the bending moment. A bending moment can be defined as the tendency of a structural member to bend due to an applied load. The larger the bending moment, the greater the internal forces and deformation experienced by the member. Using the bending moment equation shown on the slide, we calculate the maximum bending moment to be approximately 283,031 kilonewton meters. The maximum bending moment occurs at the center or midspan of the bridge. This is because the center experiences the greatest bending effect under a uniformly distributed load. After obtaining the maximum bending moment, we can calculate the maximum bending stress experienced by the eye-bar. Using the bending stress equation and substituting the values from our previous calculation, the maximum stress was calculated to be approximately 10,900 megapascals. The value represents the highest stress experienced by the eye-bar when subjected to the calculated bending moment. However, the stress was not distributed evenly throughout the member. Due to the presence of the pinhole connection, stress became concentrated around the edge of the hole. This phenomenon is known as a stress concentration and is one of the main reasons why fatigue cracks develop by the eye-bar. Next, we compare the calculated maximum stress with the yield stress of a structural steel. Yield stress is the maximum stress that a material can withstand before permanent deformation begins. Before the yield stress, the material can return to its original shape once the load is removed. Above the yield stress, permanent deformation occurs. For typical structural steel, the yield stress is approximately 250 megapascals. Comparing this value with the calculated maximum stress of 10,900 megapascals, we can see that the maximum stress greatly exceeds the material's yield strength. This indicates that the eye-bar was subjected to stress far beyond its safe operating limit. As a result, the material became more susceptible to fatigue damage, crack propagation, and eventual fracture. Therefore, the combination of a large bending moment, excessive stress, and stress concentration played a significant role in the failure of the eye-bar and ultimately contribute to the collapse of the silver bridge. Now that we have looked at the calculation and the analysis, I will hand it over to the next presenter to explain the bending curvature.
Next, I will explain the bending curvature of the silver bridge. Bending curvature refers to how much a structural member bends under an applied load. According to the mechanics of material, the curvature of a beam is directly proportional to the material's stiffness, which is presented by the product of Young modulus and the moment of inertia. In the Silver Bridge, heavy traffic loads created large bending moments throughout the structure. The I-bar members, especially near the pinhole connection, experience high local stresses due to their geometry. This stress concentration increases the bending effects and causes microscopic cracks to develop. As traffic continued over many years, repeated loading caused fatigue damage. The increasing curvature, the increasing curvature and stress around the critical section accelerated crack propagation until one eyeball fractured. Since the bridge has very little structural redundancy, this single failure triggered a chain reaction that caused the entire bridge to collapse. This shows that controlling bending curvature and reducing stress concentration are essential for ensuring the safety and reliability of engineering structures. In conclusion, the Silver Bridge collapse was the result of several engineering factors working together. The main cause was fatigue failure in a critical I-bar member, which developed from a small crack near the pinhole connection. Mechanics of materials concepts such as stress concentration, bending stress, bending curvature, and material fatigue help explain how the crack grew over time and eventually led to catastrophic failure. The lack of structural redundancy meant that the failure of a single component caused the entire bridge to collapse within seconds. This case study highlights the importance of proper structural design, regular inspection, maintenance, and considering future traffic demands during the design process. The lesson learned from the Silver Bridge disaster have significantly improved modern bridge engineering and safety regulation. Thank you. The information used in this case study was obtained from several reliable engineering and technical sources. The main references include Hibbeler's Mechanics of Materials and Gear and Goodno's Mechanics of Materials, which provide the theoretical background for stress, bending, and fatigue analysis. Additional information about the Silver Bridge collapse was obtained from the American Society of Civil Engineers, the Federal Highway Administration, the National Transportation Safety Board, Encyclopedia Britannica, and historical records from the Library of Congress. These sources helps us understand both the engineering principles and the historical significance of the Silver Bridge collapse. Thank you.